Hello and welcome to another video on projectiles. If you ever played catch with a ball, you've done some basic projectile. Let's say you're here and you want to throw to your friends over here. Now, when you were younger, you probably tried to throw the ball directly at them. You threw it straight, like so. It would fall and hit the ground and never make it. As you get older and a little more experienced, what you start noticing is that if you give it a slight upward tilt, it goes farther. And suddenly you can make the ball to your friend. If they're running down the field a little bit and you want to go even farther, you can throw it in a higher angle. And it'll go even further still. Nope. There is an upper limit to this. At a certain point, you stop getting returns. And to which point, if you throw it pretty much straight up, you don't get much distance at all. This idea, this concept, is covered by our discussion of projectile motion, but how it works and how it ties in requires a little bit of vector math. Let's take a look at this. When we start talking about projectile motion on a level surface, trying to make it from one point on the surface to another, we don't talk about throwing a football or baseball because there's the height of you above the ground, which makes it a little more complicated. Not much, we'll talk about it later, but just enough that it's not introductory enough. We want to keep it simple to start. So instead, what we typically talk about is cannons, or ballista, or trebuchets, whatever you prefer, shooting things from roughly ground level. A cannon can actually shoot things from pretty much on the ground. And when you do so, it leaves the cannon, goes up like so, arcs through the air, and crashes down here. In the previous video, we talked about how if we knew the initial x velocity, initial y velocity, we could solve the problem. And the same is true here. The problem is because this cannon is shooting at an angle, shooting up at an angle, in fact, we don't know the x or y velocities. We could generally be given or figure out the velocity it's leaving the cannon at, this v here. But that's not x or y, that's at an angle. We can't use it, at least not as is. What we'll commonly do is if we know the angle that this makes with the ground, here, let's call this 40 degrees for right now, we can use the ground as an x-axis and then make a perpendicular axis to y, like so. And all of a sudden we have a right triangle. We can break that up into x and y components using sine and cosine. And once we have done that, we can go through and do the rest of the problem. So, for instance, in this case, this cannon is firing a cannonball with an initial velocity of 115 meters per second. How far does it go? When you say how far, the first thing you need to ask is, well, how far what? Typically, what we're talking about when we talk about this is the range. How far does it go before it hits the ground again? The range is between 2 points, x and y, when the ball returns to the ground, or aka when your change in your y values are 0. Now, because we're launching from the ground, we can say our change in y values are 0. If you are slightly above the ground throwing the ball, for instance, you'd have to account for that initial difference in height, which causes some problems. So, just like the previous problem, we actually have two problems here, one for x, one for y, and the only thing they share is time. So, let's take a look at this. We are trying to find how far it goes, or our delta x value. We know that our acceleration is going to be 0. And we know that our initial velocity will equal our final velocity in the x direction. We don't know our time. Meanwhile, on the y side of things, we know that our delta y is 0. How do I know my delta y is 0? Because at the start it's on the ground, and at the end it's on the ground. My acceleration in the y direction is going to be negative 9.81. Again, the AP exam uses 9.8. This is a mistake on my part. I will correct it later. My v initial in the y direction I don't currently know. And I don't know the time. So as of this instant, I can't solve this problem. Enter the initial velocity. Because this is part of an angle, because we know the angle it makes with the ground, we can split this up into v initial x and v initial y and solve. For instance, we know that this side here is 115 meters per second. So my y, or my v initial y, over 115 is going to equal the sine of 40. Or in other words, my v initial y is 115 times sine 40. Relatedly, my v initial x, which will be the same as my v final x, is 115 times cosine. And from here, I can solve for time, and then use that time to go back here. Just like last time, we have our y, we're going to solve for our x. And we're going to be using the same equation even. Delta y equals v naught t plus 1/2 a t squared. The difference here is because my y is 0, how this ends up solving. I'm going to solve from the sine and cosine, and then plug in the numbers just to show you. When I go and plug in my numbers, I get 0 equals 73.92 t plus 1/2 times negative 9.8 t squared. And instead of going through and solving this like a quadratic, what we notice is this has a t, and this is already equal to 0. So what I can do instead is pull out a t, like so. And the first t will be 0. At time 0, it's on the ground. That makes sense. Not particularly helpful. We care about the second time it hits the ground, but time 0 is an answer. Second one, we can just solve for by saying, well, if this is 0, the entire thing will be 0. Or in other words, t equals t equals 15.09 seconds. So this cannonball will keep the ball in the air for 15.9 seconds. Once we have that, we can take it back and put it in here because the t's are going to be the same. This is 15.09 because this is 15.09. These are the same. And again, delta x equals v naught t plus, it's going to be 0 because acceleration is 0, equals 88.10 times 15, which equals 1,329.43. meters. Almost a mile. So we can see how we can find a range and how adjusting the angle would shift this problem. Now, some interesting things about this. First and foremost, one of the really interesting things is that at exactly half the distance, half your range, you're at your highest point. It's also at exactly half the time. At this highest point, we said previously when we were throwing things directly up that the velocity is 0. But in this case, your y velocity would be the only thing that's 0. Vy equals 0 here. Your Vx hasn't changed. It can't because there's no acceleration in the x direction. It's also exactly halfway between the points, provided you're firing on a level ground. Additionally, if you're on level ground, there are two angles you can shoot from that will make this land at the exact same point. You can take the low path, or there'll be a higher path. The reasoning for this will come out later. Finally, there is a shortcut we can use that we'll talk about later. With all this said, let's ask two questions. They're the same question. Number one, if I shot this cannon at a 30-degree angle, how far would it go? Do the same math. We'll talk about the shortcut after. And then also do the same for a 50-degree angle. Go ahead, give it a try. So, if you're looking at the board confused, it's because I didn't do a lot of work here. In fact, I did most of the work already, so I just went to my calculator and had it over. The delta y isn't changing, the acceleration isn't changing, and my acceleration of the x isn't changing either, and I know that my t's are going to be the same. If I do the work over here symbolically, I don't even need to change much over here. I can just plug in my vy, and I'll get a number that I can plug in here for this. So all I had to do is break this v into x and y, changing the angle. And then the rest of the problem just kind of popped out. And we get our answers up there in the top left corner. You'll notice that as the angle increases, the amount of time it's in the air increases, but not always the distance. In fact, the 40 and 50 degrees are the exact same range. This is because of how it flies through the air. If you shoot it up more, sure, it's going to go higher, it's going to be in the air longer, but it's not going to have as much x velocity to carry it forward. Any pair of angles that add up to 90 will give us the same range under the kinematic conditions, which is really cool. If you can't shoot through something, shoot over it. We can also combine these values and get a new equation. Now this equation will only work if you're on level ground, but it's called the range equation. And the way it works is we take the value we got for t here, and we plug it in here. What do I mean? Well, instead of saying delta x equals v naught x times t, I say delta x equals v naught x times this, which is negative 2 v naught y over a y. Now, we have to get a little creative here, but when we do so, this simplifies down to a very usable form. My v naught x is going to be whatever my initial velocity is times cosine of my angle. So, let's just put that in. V naught times cosine angle. And same thing here. Times negative 2 times v naught sine of my angle. And my acceleration in the y direction is always going to be g. It's always going to be negative g, to be precise. Because it's always pointing down, we're saying down is negative. Because down is negative, we get negative g. Negatives will cancel out, giving me a positive. And I have VO and VO twice. That's going to be VO squared over g times 2 sine theta cosine theta. Now, for those of you who don't remember your trig identities, 2 times the sine of an angle times cosine of an angle is actually one of those identities. Most people forget it, unless you're weird like me who remembers random things. This simplifies down to v naught squared sine 2 theta over g. Now, this equation here only works on level surfaces. The moment you have a split level, this equation stops working. But it is a nice shortcut. And from this, we can very quickly find that the best angle to shoot something at.
If we want to maximize our values for sine, we need to find a sine value that gives us a value of 1.
At what angles does sine give you a value of 1? Well, sine gives you a value of 1 at 90 degrees and 270 degrees. 270 degrees is a bit too far. But 90 degrees means that 2 times theta equals 90, or 45. If you want something to go far, Again, on a level surface. You want to aim for that 45-degree angle. Thanks for watching. Have a good one.